let's continue our discussion with the frequency and phase modulation. You see, in frequency modulation FM and phase modulation, the audio voltage controls the phase angle. It controls the phase angle of the sinusoidal carrier. Unlike AM, where the audio voltage was controlling the amplitude, now we are using the audio amplitude to modulate the frequency or the phase of the sinusoidal carrier instead of amplitude. So amplitude in the both schemes, FM and AM, amplitude remains constant. You see these two quantities, frequency and phase, they are commonly, these schemes are referred to as angle modulation scheme. Why? Because these two quantities are not much, they are related to each other. Okay? So these two schemes are not much different, they're almost the same schemes. These are angle modulated schemes. How they are related? Well, you see that frequency is the time derivative of the phase. So these two quantities cannot be varied independently. They cannot be varied independently. So FMPM are on the slightly different methods of angle modulation. You see, for example, for a carrier, for an RF carrier having amplitude A, sine of let's say it's a single tone. So let's have a sine theta t. So I have some phase, okay, which itself is a function of time. So the argument that the sine is taking is phase, and that's a function of time. Okay. Now, how the frequency is related to the phase? This is my phase. This is the phase term. Okay. This is my phase. This theta. So this theta t is a function of time, and the phase is, for example, let's say linearly increasing function of time at a rate of, let's call this omega c, which is the angular frequency of the carrier, omega ct. Then this omega c and theta are related by the derivative, the time derivative of theta. So omega c over here, you see the angular frequency is d theta, it is d theta by dt, okay, it's d theta by dt. So these two quantities are interrelated, and these two schemes are commonly referred as the angle modulation schemes, okay. So you see here this frequency, the carrier frequency, is varied with respect to the sinusoidal, with respect to an audio signal. It could be a sinusoidal, it could consist of a spectrum, it could have a certain bandwidth. So omega c has to vary. Omega c is varied instantaneously with respect to the amplitude of the audio voltage. Okay, so the audio voltage is controlling the phase of the sinusoidal carrier now. Okay, so for example, omega c, the output of the FM signal will be of the form, for example, this is the instantaneous FM frequency. Okay, that's the instantaneous FM frequency, and that is made. That's not omega c. Well, it's omega c if it is not modulated, but as for somehow this has to be made equal to, for example, k is some proportionality constant, and this is varying with respect to, let's say, sine. If we have a single modulated, a tone modulated FM signal, call this, let's say, omega at, okay, omega at, and let's say the amplitude of this is b, or whatever it is, a. So this kb is it looks like a modulation index. I mean, sine can take plus minus 1 values. So for the whatever the value of sine is with respect to t, okay, you are varying omega c. Okay, you are varying omega c. So if it is unmodulated, you don't have any modulating signal. If that is zero, then it is unmodulated carrier having frequency omega c. But if it is a modulated FM, then this becomes an instantaneous frequency. Okay, that is with time your frequency is being varied, and that variation comes from the instantaneous amplitude of the modulating signal. Okay, so that's the story of the FM.